Hi, and welcome back. I'm Elisa, and we are doing the nervous system. So this time we're looking at the brain, and not just any part of the brain. We're looking at the evolution and development of the brain, just a little, like teeny tiny bit. Like, as we go through our series, we're doing basics. All right, let's get started. So, some of the first things to think about is the fact that we're humans. And so, human brain development has been a little bit tricky to pin down. Also, being able to study the brain is a little hard because, well, so much of our recent evolution is dependent on its change. So, some of the things to think about are number one, we had ginormous heads at birth. Humans, as you can see here, these little homunculi, little cute little babies, the gigantic head, right? Actually, one of our definitions for something being what we call quote unquote cute is just head circumference size altogether and having relatively large eyes and teeny tiny cute little faces. And that all has to do with the fact that we are actually born with our brains still developing to a significant degree. So let's talk about the breakdown of that development. So I'm going to kind of go back and forth between a couple slides. So let me go ahead and just start here. This is embryo at 1 month, right? An embryo later on at 5 weeks, and this is a smaller child. So as you can see, what ends up happening as we're developing in utero is we have this kind of linear structure, and it goes rostral to caudal. So rostral, think of like a rooster, like the beak of a rooster, right? And then caudal actually means tail. So think of it meaning like tail. So that's kind of some important directionality we're going to look at. So as we move from rostral to caudal, we'll see that the spinal cord begins to develop and remains kind of, as we can see, that linear type tube shape, right? But what ends up happening kind of in the center components here is we start seeing more and more complexity, more definition. It actually is going to deviate from forebrain, midbrain, and hindbrain into some more complicated structures, and we'll look at that in a little bit. As you can see, as we're even just a small child, right? So human brain development really doesn't completely finish fusing until around your mid-20s, and some people would argue doesn't actually finish up until probably your early 30s, which is really a long time. As you can see, it still has a great degree of complexity even as a small child. So I think what I'm going to do is I'm going to go to the next slide, and we're going to go ahead and start looking at some of these structures as they begin to divide and what we call specialize, right? So each one of these regions are going to become specialists. Okay, here we are. So this is back at embryonic development. And so what I wanted to do is, I brought you there first because I wanted you to kind of get an idea of where we're going with this. But this is some of the earliest stuff. So rostral, remember this is up near the front, right? Think of, right, like the beak of the rooster is here, right? If you're a rooster, you'd be looking that way, and then your rooster tail would be caudal that way, right? So that's the development. As you can see, it's a single tube. You'll hear this a lot. It's the neural tube. It contains what we refer to as the neural canal, which we'll get into some interesting things of that in a bit, especially when we talk about cerebral spinal fluid and the aqueduct concept. But for now, neural tube development begins super duper early. And this is one of the reasons it's incredibly important for women who are of childbearing age or possibly trying to get pregnant to have proper nutrition, which is something we'll talk about later on. But so we begin as a single tube structure, just like everything else in the whole body. We are basically worms and series of tubes that can generate complexity over time or develop complexity over time. So the term encepha, right? So you're going to see this a lot, like here's rhombencephalon and mesencephalon, right? And this is, all of this is referring to, comes originally actually from Greek, right? It's originally Greek text. And so let's see, here's like encephala, right? So the in means literally like in, right? And then the cephala, there's actually the Greek terminology we believe is like it starts with a K, but it means like just, in the head, right? Like, so this is like the head. Okay, so that's the etymology of that. So that's the oldest part of our definitions. anyway, so continuing on, whenever we see pro, think like out in front. Mes maybe middle, right? And then rhombo is kind of different. Rhombo, like think more of like, like a rhomboid type structure, right? So that's like actually more so for the physical presence. So these are the primary regions, three regions, which will become the forebrain, the midbrain, and then the hindbrain. Okay. So when you think about let's start with the hindbrain actually, because most folks feel that that's kind of like the older part of it. Think of brain stem for the most part, like some of the brain stem division is going to be here. And a lot of work is going to go into developing these two regions, right? So there's the hindbrain proper, which is going to be closer to spinal cord. This is where medulla oblongata is, a whole bunch of our cranial nerves are going to be coming off of these regions. Also, we're going to be looking at the midbrain proper, which is going to be like a transitional point to this like area that we just added all this complexity into, right? So kind of going back when we're looking at the brain here. So look how much we actually ended up investing in this area, right? So here's like, here's pons and medulla oblongata, and here's our midbrain. Let me get a different color. There's like a lot of yellow. Okay, right? Like here's all that right here, right? And so here's midbrain, hindbrain. And if you look at how, like the percentage is so much higher, the proportion, right? And forebrain is super tiny for like the longest time. And then all of a sudden, wham, bam, humans just get nutty with it. Well, not just humans, but definitely we were one of the ones that did. Okay, so going back in. So what happens is diencephalon and telencephalon are going to develop into these like two distinct regions. Like one is the diencephalon. So think of this as like the router, right? So if we have, your brainstem primarily communicating information about, basics like body temperature, sensory information, right? Kind of a highway for that. The diencephalon is a little bit of like a router, right? So thalamus, for example, is going to do stuff like, send signals, sensory signals to the right part of the brain, and then, maybe motor signals out from the right part of the brain through the brainstem, right? So it's routing. And then things like hypothalamus out here, this is going to be, like temperature regulation, or in some cases, regulating things like vasopression, which is going to be, controlling like the water out, or the amount of water that's circulating in the blood, right? So it's kind of, what else? Oh, sleep, all kinds of good stuff, right? And then here's the interesting one. I love this retina. Retina's in there. It's an oldie, but it's a goodie, right? So it's in there deep. The one that's kind of interesting is telencephalon. So telencephalon took on a whole new like life, right? And became the cerebrum, right? So cerebrum, cerebellum, these are all about like 16th-ish century terms, referring to the complexity in the brain that's responsible for doing stuff, decision-making centers, right? So we'll get into that more so, but as you can start to see, the telencephalon starting to get a lot bigger, and then by the time we're, boom, developing, right? So here's telencephalon here, so tiny at 5 weeks, and then by the time we have a more fully developed brain as children, wow, lots of complexity here, lots of real estate, very large, but also we're going to talk about some of the phenotype of the brain as it develops, right? Like, do you love how I'm putting arrows on yellow with yellow? That's cool. Yep. I'm using my cerebrum for that decision there. That's not good. Hey, let's talk about cerebrums. This is a mouse. Okay. They're great. We love mice. And it's also it's a good model for studying brains. It's not the best, and we'll look why. Humans' brains are the best for studying human brains. But anyway, that's another story. So here's some of those basic structures we were talking about. So here's brain stem, right? And then midbrain would be in here, and there's cerebellum. And then I want you to just give a minute to just, let me tell you what okay, right up here, this is olfactory, right? In mice, they're using their sniffers a lot. So quite a bit. Oh, this is great. Look at that. There's like some pons, some medulla oblongata in there, right? Here's the brainstem going up, right? But here's that telencephalon region coming off the side, right? Either hemispheres of the brain. One thing that's very different from a human brain, as you can see already, where are all the wrinkles, right? What happened there? So that's another step of human evolution and development is very important. So many animals have like kind of a more smooth surface to the brain, whereas humans have a super wrinkly one. So let's take a look at this. Fuzzier slide than I'd like, but there it is. So here is, where is it? Oh, that's our mouse brain. Remember, we looked it up close, so you can remember it's pretty smooth and flat. Here's our human brain, because I know you're already looking at it, like the complexity and the folds and the ridges. And so like the whole point of that, and we'll get into it a little bit later, is to make more space for gray matter. Gray matter, if you remember, or can go over some of my other videos, that's where the active neuron bodies are. And the white matter, think of that, that's where the axons are. That's like all the communications. So here's, like a cat, a little bit smarter than a mouse, huh? Definitely. Oh, sorry guys, sorry cat lovers. Look at that dog brain. It's looking good, looking pretty good. Here's a monkey, right? So we are primates. Monkeys, macaques are also primates, so there's definitely more complexity in here. But then check out when we start looking at other primates, a gorilla brain and a human brain, right? This is not relative size, obviously, but what is kind of interesting is we start seeing these a little bit more ridging, more familiar folds, right? So that's kind of something that is preserved. And then just, for fun, just to kind of get you guys thinking about thinking actually is, so now I want you to take a look at elephant brain and then dolphin, right? So these are all the sulci and gyri, right? These are all the creases and the folds and the ridges, and we'll look at that in another video. But there's so much more, so many more folds. So that kind of gives you an idea of scale for potential intelligence in some of these animals, or at least some evolutionary complexities, because we knew, dolphins and elephants, they are up there with intelligence. So, just something to think about. So, other things we'll look at, and you kind of remember this back, and I should have put the skull in there. But when we talk about things like the skull, right? So you might remember, here's like a baby face skull, right? And here we go. Right, so if we're looking at human skull, and here, let's get a max in there, a bit more space on that max, right, hook it in temporal. All right, there we go. One of the things you might remember is that as we look at the younger, like fetal skulls, and we look at some of the young children's skulls, we see a lot of these like kind of suture lines, right? And so these are these membranes. So our brain is going to go faster than the surrounding skull. And so we have these nice membranes, right? So these membranes are going to help expand. So that was, kind of what that was about when we were looking at that way back during the skeleton. So the other thing to think about is, although it keeps growing and we do need to make more, space for that cranium altogether, there comes a point where we can't even, if we were to expand completely to where we were, flat like a mouse brain, we wouldn't even be able to fit in the skull. I can't even imagine, right? And like, gosh, that makes you start thinking about elephants and dolphins as well, come to think of it. But anyway, so we're going to have to fold, and the more folds we have to accumulate just to fit into that available space. And that's one of the things about humans is we have things like, if you look at a lot of other primates, they just, here's like eyes, and then and then like backs, and then, right, and then jawline, right? It's kind of a longer jaw than I was expecting, but here's the skull casing on it, right? What's missing? I'll show you what's missing, a forehead. Humans actually had to expand our cranium, and we had to get taller just because we had no other directions to grow in order to be able to still fit through a birth canal, right? So let me see. Was that, look, yeah, see, do you see it now? Yeah, okay. Cool, well, speaking of all of this stuff, I just wanted to say, thanks for joining. I don't know, I usually do like a happy face. We'll do it over here. Oh my gosh, here it is. So much better. All right, here we go. Depersonalize my poor skulls. All right, well, thank you so much for tuning in, checking this out, and learning just a little bit of some of the basics about brain evolution and development, some of the regions of the brain. And Have a great evening. Bye.